Earthquakes belong to those natural phenomena that can cause humanity the greatest harm. People have tried to predict them ever since. The first scientific attempts in prediction were, however, undertaken in the 20th century with the development of modern seismology. Scientists have tried to predict earthquakes based on so-called precursors, such as ground deformation, seismic waves velocity changes, radon emissions, electromagnetic anomalies, and behavior of the animals. If we are not prepared for these extreme events, they can cause great loss of human lives and losses for our economies. In 1975, Chinese seismologists successfully predicted the Haicheng earthquake based on the precursors, and therefore, the Chinese officials ordered that the city of Haicheng to be evacuated. The prediction of the Haicheng earthquake was considered as being a great success of seismology, and many believed the earthquake prediction problem was solved. However, soon other powerful earthquakes happen all over the world, that scientists were unable to predict them. Therefore, the seismologists undertook immense efforts to better understand the earthquake physics and associated phenomena. Numerous models of faulting, earthquakes, and scaling laws for the earthquakes have been developed, but still, no one was able to reliably predict them. In 1997, a group of leading seismologists published now a famous article in the Nature journal, entitled, "Earthquakes Cannot Be Predicted." This article threw a dark shadow on the earthquake prediction problem. However, the situation has dramatically changed in the first 2 decades of the 21st century. Decades of massive efforts by seismologists all over the world have finally brought us to the solution of the earthquake prediction problem, which is an entirely new physical theory of earthquakes. We call the omega theory. The omega theory is based on observations by structural geologists, which discovered that faults form groups that tend to be parallel to each other. A group of parallel faults is called a fault set, and a group of fault sets is called a fault system. Fault systems are therefore highly organized structures within the Earth's crust. The spontaneous question then arises: what are earthquake time series along the parallel faults? The answer to this question can be found either by theoretical consideration or by observations in nature. Both approaches point at the same conclusions. Earthquake series along the parallel faults are never random, but are either periodic or geometric. This finding of the omega theory explains a vast number of observations made by seismologists after the year 1999, who discovered the so-called repeating earthquakes sequences, RES. In the omega theory, such earthquake series are called the omega sequences. The easiest and the most effective way of illustrating how the omega sequences work is an example of the falling dominoes. If all dominoes are of equal size, the sequence of events is periodic. But if the dominoes form a geometric series, then also the sequence of events is geometric. Thousands of such periodic and geometric omega sequences are constantly occurring in the Earth's crust in all seismic zones along tectonic plate boundaries. They, however, do not run independently, but interact each with other. The existence of these interactions among the omega sequences has led to one of the greatest theoretical breakthroughs within the omega theory. It was discovered that the omega sequences synchronize their rhythm, and sometimes produce a large event at the same time. This is a well-known phenomenon in theoretical physics called chaotic synchronization. A growing number of seismologists and research groups now think that the phenomenon of synchronization and triggering of earthquakes are two sides of the same coin. Scientists also discovered that the phenomenon of the chaotic synchronization is a path to solution of the earthquake prediction problem. The second major concept of the new theory is the concept of tectonic waves, which was developed already in the second half of the 20th century. Again, the best everyday analogy with tectonic waves is an example of the falling dominoes. When one domino falls, all subsequent dominoes will also fall, leading to a wave of collapsing dominoes. In the Earth's crust, the dominoes are tectonic faults and blocks of rock, and the domino effect in the Earth's crust leads to the so-called tectonic waves, sometimes also called the strain waves. These waves have all possible velocities ranging between 0 and approximately 6,000 meters per second. Based on a careful analysis of the distribution of past earthquakes on Earth, we can calculate the current and the future positions of tectonic waves. When these waves pass through the active fault systems and the plate tectonic boundaries, they can cause strong earthquakes. Therefore, tectonic waves define endangered regions, where dangerous seismic states can occur. The seismic states can be illustrated on charts as clouds, which is a very similar approach to that used in meteorology. In 2018, after the publication of the Omega theory, a group of physicists and geologists initiated the project Quantectum. This project is dedicated to advance the global earthquake prediction and ensemble forecasting. Classically, numerical earthquake prediction was supposed to be based on a single, deterministic prediction. However, this approach is not used by Quantectum. Seismic systems are chaotic. Therefore, Quantectum uses several models to predict or forecast earthquakes. For each model we produce numerous forecasts, all activated from the same starting time, but with slightly different starting conditions, and by using slightly different physical parameters. In this way, we produce ensembles of forecasts for each model. Ensemble forecasting is a type of probability forecasting. It conveys a message, which explicitly reminds the user about the forecast uncertainty that should be considered and taken into account when making any practical use of the forecast. The uncertainty associated with every forecast means that different scenarios are possible, and the forecast should reflect that. Single deterministic forecasts can be misleading as they fail to provide this information. In this way, Quantectum can produce charts of synchronization clouds, which indicate regions of increased probability for the moderate to strong earthquakes on a daily basis, up to 64 days ahead. Knowing what the seismic activity of tectonic zones would be, contributes considerably to our economic growth and the maintenance of our modern lifestyles. Seismic safety is one of the major factors for the well-being and development of society, with an impact on all scales from individual lives to global economies. For long, scientists thought earthquakes will never be predictable. But with the Omega theory, the seismology of the 21st century has finally put a step on the path that meteorology is walking for several decades. The new theory has finally allowed us to build the first semi-autonomous computer system, called T-Tecto, that allows for reliable and effective global ensemble earthquake forecasting and sometimes also predictions on a daily basis.